This is lesson 6 of unit 13, the last lesson. And this whole chapter has been about solutions, and now we're going to take a look at some mixtures that are not solutions. So not everything that's a mixture is technically a solution. So the first one, as you'll see, is milk. Milk is actually not a solution. It is actually what's called a colloid. Now the difference, as you'll see, is that the particles in milk are actually bigger. So the water molecules don't dissolve them. There's no dissolving happening. It's more the particles are hanging in the solution. The particles are much bigger. And it all has to do with dissolving. You have to dissolve in order to be a solution. So let's go ahead and define this colloid idea. It's large particles that hang in the solvent. But here it says they cannot be filtered out. So if you pour them through a filter, they'll actually go right through the filter. And so milk actually cannot be filtered out. So the particles are still hanging in the solution, and they can't be filtered out. Paint is another example of this. And actually foam is another example. Foam is really a colloid, and it's actually a type of colloid that has a gas dispersed in a liquid. And fog is actually a colloid. It's a liquid, believe it or not, a liquid dispersed in a gas. So fog is little tiny droplets, water droplets, hanging in the air. So technically all three of these, even though they may be perfect mixtures, they are not considered solutions, they are considered colloids. And there is one experimental way to check, and that's called the Tyndall Effect. The Tyndall Effect says that in a colloid, the particles will scatter light and make a light beam visible. So you have, for example, two mixtures here. The first mixture, you can't see the laser beam through the first, but through the second, I don't know if it's easy to see in your notes, but here is the laser beam. And this laser beam, the reason we see it is because the light particles are bouncing off of the particles in the solution, coming back to our eyes, and we're able to see it. If we're able to see it, that means the particles are big, and it's technically a colloid. So this would be a colloid, and this would be a solution. And that's really the dividing line between them. You can also see it here with the regular flashlight. This mixture here scatters the light. This one does not. I know there's maybe a little illusory effect to make you seem it does, but this is a solution then, and this is your colloid. And many substances in life are colloids, even though we may refer to them as solutions at times. And this is also why you see early morning on maybe a spring or summer day, usually summer day, you see the light rays. The reason you see light rays through it is because the air is a colloid at that point. And the colloid is because the water vapor is hanging in the solution. Now, whenever it heats up, that colloid actually will become a solution in the daytime. It will become a solution. So this is like a perfect dividing line between the two, colloid and solution. Okay, and then the last definition that is even less of a solution is called a suspension. And a suspension has very large particles that hang in the solvent, and they can be filtered out. So an example is muddy water. If you shake it, you may shake it for it to be uniform, but this is really more of a heterogeneous mixture. Heterogeneous. Whereas the other two were homogeneous, this is more heterogeneous. So it'll settle to the bottom if you leave it, or you can easily filter it out. And these are suspensions, is the idea. Okay, so we kind of came around. Last thing we'll talk about is something called heats of solution. So we've demonstrated this in class, but anytime you make a solution, there is an energy change associated with it. And this is because, as you'll see, bonds are involved. So intermolecular forces are involved. So we're breaking bonds, we're making bonds. Here it says the energy change is usually small, but we did see with some compounds like sodium hydroxide that the energy change is very significant. With acids and bases, this is an acid, recall, this is a base. With these two compounds, the energy change is quite significant. So we'll take a look at this shortly. And the thing to say is anytime you are breaking bonds, this is an endothermic process. Remember that endothermic means heat is going into the system. And then whenever you're making bonds, this is an exothermic process. Heat is going out of the system. And this makes sense because if you want to break a bond, if there's a bond between two atoms, you want to break it, you have to put energy into it. And then when the bond is made again between the two, energy is released to you. And this is exactly what happens. So both things have to be combined. Anytime you make a solution, we looked at this picture earlier, this is salt, this is sodium and chlorine, and there's a bond between these two ions. So what happens is this bond has to be broken, this bond has to be broken, this bond has to be broken, and then a new bond has to be made, and that new bond is between the water molecules and the salt. These new bonds must be made. And what we'll say is we'll calculate the amount of heat that's released here, or that would be absorbed when you're breaking it, and the amount of heat that's released here, total that up, and find out what the overall picture is. So here it says, if more energy was released when bonds were made than took to break them, the overall process is exothermic. So it released more heat than absorbed, overall it's exothermic. But the opposite is true, the process is endothermic. And this all depends on the strength of intermolecular forces. So this is kind of the big term. We've been using this term for the 2 chapters, and we're going to finish up this chapter 13 with this term, intermolecular force. It's all about the forces between the particles. These are physical changes that we've been talking about. Okay, so this completes for us lesson 6 and chapter 13.